Tectonic movements and the formation of primary gold deposits. The story of primary gold deposits begins deep within the dynamic architecture of the Earth's crust, where enormous tectonic forces relentlessly stretch, compress, melt, and recycle rocks over hundreds of millions of years. These forces are not random. They follow patterns shaped by plate boundaries, subduction zones, rift zones, and continental collision belts, all of which create unique geological settings that allow gold to concentrate from scattered trace amounts into economically valuable deposits. One of the most influential environments for primary gold formation is the subduction zone. Here, oceanic crust loaded with sediments, volcanic rocks, and mineral-rich layers gradually descends into the mantle beneath a continental plate. As this slab sinks, temperatures rise and water trapped within the minerals is released. These fluids become highly pressurized solutions, capable of dissolving small amounts of gold and other metals locked within the descending material. Driven upward by buoyancy, these hydrothermal fluids migrate through fractures carved by tectonic stress. As they ascend, the fluids encounter lower pressures, cooler conditions, and chemically reactive host rocks. These changes force the dissolved gold to precipitate, crystallizing into veins that later become targets for modern mining operations. Above these subduction zones, volcanic arcs emerge, towering chains of volcanoes fueled by the melting crust below. The magma feeding these eruptions serves as another essential mechanism for transporting dissolved metals. As magma cools beneath the surface, volatile components separate from the melt, forming mineral-rich fluids that travel outward through fractures, fault lines, and zones of weakness. Depending on depth and temperature, these fluids create distinct deposit types: epithermal systems, formed at shallow depths with low-temperature fluids, and mesothermal or orogenic systems, formed deeper within the crust under high temperature and high pressure. These variations explain why gold can appear in environments as different as mountainous bedrock, volcanic plateaus, or ancient metamorphic belts. Over tens of millions of years, tectonic movements also help expose these deep deposits. As continents collide, mountain ranges rise, carrying once-hidden gold veins closer to the surface. Conversely, rifting and stretching of the crust may erode mountain peaks, peeling away layers of rock and revealing the mineralized zones within. The rocks that once confined the gold may be worn down by weathering and rivers, beginning the cycle of creating secondary placer deposits downstream. In summary, primary gold deposits are not the result of a single geological event but the consequence of Earth's long-term tectonic evolution. They are born from the intense pressure of subduction, enriched by volcanic fluids, shaped by fault systems, and later exposed through uplift and erosion. Each deposit is a geological archive, evidence of ancient oceans swallowed, mountains razed and destroyed, and continents reshaped by the powerful machinery beneath our feet. Erosion, transportation, and the birth of secondary, placer, gold. The formation of secondary or placer gold deposits is a testament to the unending power of Earth's surface processes, forces far quieter than volcanic eruptions or tectonic collisions, yet equally transformative. While primary gold forms deep within the crust, placer gold originates after these deposits are slowly dismantled by time, climate, and the elements. Over millions of years, mountains crumble, rivers carve new paths, and wind reshapes the landscape. Through this continual reshaping, gold, one of the most chemically stable and enduring metals on Earth, survives the destruction of its host rock and begins a new journey. The process begins with weathering, the gradual breakdown of rock exposed at the surface. Chemical weathering dissolves weaker minerals, while physical weathering, freeze-thaw cycles, root expansion, thermal stress, fractures and collapses rock structures. When quartz veins carrying gold are exposed, these processes release individual particles, flakes, or nuggets. Gold's resistance to corrosion means that rather than dissolving or oxidizing, it persists in its native metallic form. As a result, gold liberated from primary sources remains chemically intact, ready to be carried by gravity and water. Gravity plays an immediate role. Because gold is denser than most surrounding minerals, over 6 times heavier than quartz, it tends to migrate downward through fragmented soil and sediment, accumulating in cracks, crevices, and bedrock depressions. But its most significant migration begins when water enters the picture. Streams and rivers become conveyor belts for gold particles, transporting them from their original source into floodplains, sandbars, and riverbeds. During high-energy events such as floods, swift currents carry gold along with sediment. As the water velocity drops, around bends, behind obstacles, beneath waterfalls, heavier particles settle first. Over time, these deposits create placer concentrations, the richest of which may become economically valuable gold fields. The shape, size, and texture of gold grains reveal clues about their journey. Angular particles suggest short distances of transport, while smooth, rounded nuggets indicate long, turbulent travel downstream. Some gold becomes trapped deep within the sediment layers, preserved beneath gravel beds and ancient river systems long after the river's course has shifted. These buried channels, known as paleoplacers, can become hidden repositories of gold that modern geologists and prospectors seek using mapping techniques, drilling, and historical topographic analysis. Wind can also contribute to placer formation in arid environments. As lighter sediments are carried away, heavier materials, including gold, remain behind, forming desert placer deposits. In coastal settings, wave action concentrates gold within black sand layers, often alongside magnetite and other dense minerals. Ultimately, the birth of secondary gold deposits reflects the delicate balance between destruction and creation. The same forces that erode mountains also redistribute their wealth. Rivers sculpt valleys, glaciers grind bedrock into powder, and shifting climates determine where gold settles or is re-exposed. Placer deposits are snapshots in time, records of ancient landscapes, vanished waterways, and past climates. Through erosion and transportation, gold's journey becomes an epic story not only of geological transformation but also of human fascination, as these deposits have fueled exploration, migration, and gold rushes that reshaped economic and cultural history across the world. Decoding geological clues. How modern geologists discover hidden gold. Discovering hidden gold today is far more than a matter of luck, intuition, or traditional panning. It is a scientific investigation rooted in geology, chemistry, physics, and an ever-growing arsenal of technological tools. Modern gold exploration blends the ancient language of rocks with advanced analytical techniques, transforming landscapes into coded maps filled with clues waiting to be interpreted. Each mineral grain, each fracture line, and each subtle shift in soil chemistry becomes a piece of evidence in a larger puzzle that guides geologists toward buried gold systems that may be millions of years old. The first stage of discovery begins with geological mapping, the art of reading terrain as a history book written in stone. Geologists study mountain belts, volcanic arcs, and ancient fault zones to identify regions shaped by tectonic processes known to generate primary gold deposits. They search for structural traps, fault intersections, shear zones, folds, where hydrothermal fluids once flowed and cooled. Mapping also reveals rock alterations such as silicification, serpentinization, carbonatization, or argillic changes, each signaling that mineral-rich fluids passed through the area in the distant past. These alterations may not show gold on the surface but act like fingerprints left behind by a geological event. Once an area shows promise, geologists transition to geochemical exploration, analyzing soils, stream sediments, and rock fragments for elevated concentrations of elements associated with gold. Gold itself may be too sparse to detect easily, so professionals search for pathfinder elements, which include arsenic, antimony, tellurium, mercury, and tungsten. These elements form halos, chemical shadows that surround gold deposits. By studying changes in these chemical patterns, geologists trace the path of the mineralizing fluids backward, narrowing the search toward a potential source. Each sample taken from riverbeds, hill slopes, or drill cores refines the picture and tightens the boundary of potential gold-bearing zones. Advances in physics have revolutionized exploration through geophysical surveys, allowing scientists to see below the Earth without excavation. Magnetic surveys detect buried volcanic structures and faults. Resistivity and induced polarization reveal zones where electrically conductive minerals gather. Gravity surveys identify dense bodies hidden beneath sediment. Meanwhile, satellite imaging and drones equipped with multispectral and thermal cameras scan vast terrain with precision unimaginable a generation ago. From a bird's-eye view, changes in vegetation health, soil moisture, and heat emission may signal underlying mineralization. When enough evidence accumulates, drilling becomes the decisive test. A drill core acts as a time capsule, bringing up cylindrical samples from hundreds of meters below. These cores tell the complete geological narrative: the pressure environments, fluid pathways, mineral chemistry, and deformation history. Under the microscope, thin sections reveal gold trapped within quartz veins, bound to sulfides, or liberated by weathering processes. Laboratory analysis determines grade, tonnage, and whether a deposit is economically viable. Yet modern exploration is also shaped by sustainability and regulation. Environmental impact studies, engagement with local communities, and data-driven resource management are now essential components of responsible gold discovery. Geologists today are not only explorers, they are interpreters of complex Earth systems tasked with balancing economic opportunity and environmental stewardship. In essence, the discovery of hidden gold is a journey that begins with questions carved into the landscape and ends with answers extracted from deep within the Earth. It is a fusion of ancient geological processes and cutting-edge science, a field where solving the mystery of what lies beneath requires patience, precision, and the ability to read the invisible stories written in the rocks beneath our feet.